Good afternoon, everybody. The speaker today is Sudipto Pataniak. He did his PhD in India, in Calcutta, in the Bose National Center for Basic Sciences, in things related to collective motion and the V-shaped model. Yeah. And then he moved to Paris to the group of Fernando Peruane, who was here around this morning, and working essentially in problems related to active matter, collective motion, collective behavior. Thank you, Sudipto.
Yeah, so thank you. Good afternoon, everyone. So before I start, I want to thank Professor Cristobal Lopez for giving me opportunity to talk in front of you. So the title of my today's talk is Cluster Formation, Order, Aggregation in Active Matter, and Different Classes of Active Phase Separation. So this work has been done in collaboration with Professor Fernando Peruane. And so before I start, I will briefly introduce about definition of active matter system. So in this system, we study ensemble or collection of actively moving particles. So then question comes in mind, what is an active particle? So these are particles who can convert their internal energy into a mechanical force or the systematic motion in a dissipative medium. And there is a wide range of examples of active matter system. It can be biological system and also the artificially made active matter system like chemically driven particles, colloidal particles, then also the colloidal like magnetically driven Quinker rollers. And there is a lot of examples in biological systems like ant, fish, sheep, what things of work Fernando does with the experiment in our group, and also like different kind of cells, cell immigration and all. So now the motivation of today's talk is to talk about the phase separation phenomena of the collection of this kind of active particles. So I start with this work in 2012 by Philly et al. They proposed a numerical model and theoretical study about the persistent active particles. So to understand what is the persistent active particles, if you look at these particles, they have a polarity, they move along this preferred direction, and they are disk-shaped particles. So, and because of the persistent dynamics of these particles, they do phase separate. And now you can see what is the interesting phenomena of these particles. They can phase separate and way below the packing fraction compared to their equilibrium counterpart. And now if you consider very high packing fraction, they will make a big cluster like a liquid drop in a background of dilute gas. So then year after, there was a kind of experimental realization of this kind of phase separation by Buttononi et al. And you see, they consider these persistent active particles or colloidal particles, and you see there is a formation of big clusters, and there is background gas, dilute gas in the system. And there is a lot of examples of which are compared as this kind of phase separation, like bacterial system. Here I'm showing one example of Mesococcus xanthus bacteria. So I should like introduce what are these bacteria. They are motile. They have this like they are considered as active particle. Now they have an interesting property. Like if you put them in a substrate with some nutrients, over the time their activity slows down. So they do form the domains, and the phase separation phenomena is compared to the like motility induced phase separation. So one can calculate how the domain size or coarsening is growing for this system, and that is similar to the MIPS kind of phase separation behavior. So far the systems I have talked about, they are scalar active matter. So one can characterize the phase separation phenomena for this system defining a scalar order parameter. So now the thing, what are the other kinds of active matter system other than the scalar active matter? Also, the one question came to our mind, like all the phase separation in active matter are MIPS-like, or there exists a different kind of phase separation for this active particle system. So we are doing a kind of an experimental collaboration with Professor Julian Simpson in TU Dresden. They have the experimental setup of TiO2 gold-coated Janus particle. They are active particles. And you see there is a phase separation in the process. So if you are interested, after the talk, I can discuss a bit of this kind of project. But I put this example here just to show, because this phase separation is different kind compared to the MIPS. Because in MIPS or motility-induced phase separation, we need a critical packing fraction to have the phase to perform the phase separation. But these systems are very dilute. The packing fraction is way low, And there is attraction mediated phase separation. So this is not MIPS-like, and the properties of particles are quite different. I will explain that in next slide. And also there are many other groups. Yeah.
Normal phase separation.
Yeah.
What is it about?
Yes, so if I go back the previous slide, so here we have the noise term. So I should have explained a bit. Okay, so this is the position update equations.
There is phase separation.
Yeah. Yeah, it's a persistent length or the persistent time of the particles. So that we can define with the d theta, not eta theta. So these particles are persistent, so they will move in a particular preferred direction until like they have a defined persistent length. So one can tune this noise to increase or decrease the persistent length of the particle. Yeah, and noise we can consider as a temperature of the system. No thermal effects. Yeah. Yeah. So this is the different kind of particles and their phase separation. I will talk about a bit about the nature of the particles or the dynamics of the particles. Also, there are other examples of like different the bacteria. Like they have, you see, this is an example of meningitis bacteria. So they have the pili, type 4 pili, and when they come close, they can glue with the pili. And this kind of interaction can be mapped as an attraction mediated interaction. And you can see here they do form clusters, and inside the blood like vesicles, they can block and they can make the clusters, and they do phase separate. They perform the phase separation phenomena. So the conclusion is from this part, so there exists some other kind of phase separation that is mediated by attraction in active matter system that is not similar to the MIPS-like behavior. So now what I was talking about, the particles we are working on also, you can see like if you follow this trajectory of the particle, they do rotate. And they can change the direction of rotation. So they are not chiral. So over a long trajectory, the direction of the rotation changes. So I can play this video again. So if you look at this one, they're rotating kind of clockwise. Now this counterclockwise. And one can look at the angular velocity. They will have a distribution mean around 0, and they rotate in the both directions. So this is not the persistent Brownian particle, and their phase separation phenomena is different compared to the MIPS-like behavior. So far I talked about the scalar active matter and the phase separation in scalar active matter, but there exists another kind of active matter system where we know there is an emergence of ordering in 2 dimensions. In 1995, Vicek et al. They introduced a novel model to understand the emergence of ordering in this kind of system in 2 dimensions, which is not in equilibrium system. So now this is one of the result by Sate et al. In 2008. They consider this kind of Vicek-like model, and you can see there is a formation of bands. It's a numerical study, and there is a phase separation phenomena also. So this is 2 things happening in this system. One is phase separation, another is the emergence of order. And these bands moves in a direction that is shown by this arrow. So now what are the interactions for this particle? So they are self-propelled particles moving with the speed. And now if you start with a random distribution of particle, they do velocity alignment, they do collective behavior, and there is a noise in the system, so that will not be a perfect alignment. So there is some noise in the system. So this system, in presence of velocity alignment, they do phase separate, then there is emergence of ordering. Now one can understand this emergence of ordering in terms of writing the hydrodynamic equation for density field and polar order, like the velocity field or the polarization field P. So polarization is the V naught, which is a constant, and the direction vector of the velocity field. So, and there we can understand the emergence of ordering in the system, and so these are the terms that gives rise to the ordering of the system, or the polarization of the system. So far, people like the community in our community mostly understand all the different active matter system as this universality class. So now this comes to the motivation of the today's talk. So is there different classes of phase separation in active matter system other than this kind of system what I have talked about? Also, the phase separation phenomena is going to change if we consider the emergence of ordering in the system. So now I come to our study. So we start with a simple model of diffusive active particles, persistent active diffusive active particles. So I play this video first. So you can see they have initially they are randomly distributed, and the orientation, this arrow shows the orientation of the particle. And what is the model here? I should explain that. So we consider this is the cell active force term. So the particle move with the cell propulsion speed v naught, and this represents the unit vector or the direction vector of the velocity of each particle. So this is the position update equation of an ith particle. And this is the interaction between each particle pair, that the potential or the force. So this is the potential, this is the force or gradient of the potential. So now it's a spring force. The interaction is the attraction among between the particle pair. So this is a short range force. So there is a cutoff at the distance. So interaction radius. This is the interaction radius. So particle do interact inside that interaction radius. Beyond that, they will not interact with each other. And because of this is the harmonic potential attraction. And because of the attraction, whenever they meet, they will glue and they will form the clusters. And this is point particle. So yeah, and this is the theta. So the orientation of each particle is randomly. We start with the random orientation of for each particle. Now, one thing I want to point out in this video. So if we start from the initial random distribution, and you see they glue and they make cluster, but the dynamics of the cluster is slowing down as the cluster is growing in size. So I will describe why this phenomena is happening. But before that, so we consider the attraction among the particle pair. So it's like whenever particle come close, see the neighbors, they try to come close because they want to follow some, they do interact and they come together. So that because of there is no volume exclusion, the point particles, they will come and they will get localized. So if you wait a long time, so there will be only one cluster and all the particle will be localized. So there is no cluster cross section. So they will. So this leads to the aggregation that we can call as a condensation. So the size of the cluster is less than the size of the interaction radius, and all the particles will be condensed, like they will glue, will come together and will be localized. So this is kind of a color bar is exponential of the local density of the particle. So that's why, because otherwise all the particles, so this is all the particles are coming into this cluster, and it will end up only one cluster with all the particles. So this will be a huge color bar. So that's why we are making this color bar kind of exponential function. So now, so system in presence of attraction, all particle will come and they will form condensate. So now the kind of motivation from this part is to understand the behavior of the clusters depending on its size, also how the coarsening happening when the clusters glue and they over the time. So now first we calculate numerically we calculate the diffusion constant for, so we start with 2 particle cluster, 3, 4, 5 like this, and we are calculating the diffusion constant of the cluster, and that is linearly decaying with the size of the cluster because they are diffusive cluster, they will glue and their diffusion constant will decay. So one can actually understand why this is linearly decaying. So these are the polar particles, they have the orientation or the velocity vector. So this is the polarization one can calculate depending on the orientation of each particle, and you can sum it over all the neighbors in the cluster and normalize with the total number of particles. So then you can write down the equation of motion for the center of mass of that cluster. You consider a cluster as a metaparticle, and this polarization order parameter decays with the size of with the exponent -12 with this size. And that explains one can use the Green-Kubo relation, and that will lead to the diffusion constant which is linearly decaying with the size of its cluster. So now next thing is how the coarsening happening in this system. So we start with the random distribution of particles. So let's say there is m number of clusters in the beginning, and because of the attraction, number of clusters will decrease with the time. So one can, so MT is the number of clusters at time t. So one can define the average cluster size at any time. That will be total number of particles over the number of clusters. And now one can, so there are M clusters we can consider as M diffusive particle. And we can write the diffusion equation. So this is the density, this is the average mean square displacement for the clusters, and that in the 2 dimensions that will be 4d tau, t or time. And then you can estimate the time, average time needs between the collisions. So that goes proportional to the 1 over m square, or the number of the clusters. And then we can propose the mean field, like mean field calculation for the cluster evolution equation, and that leads to the exponent minus half. So coarsening for the diffusive clusters in presence of attraction, we get the exponent half. So far I talk about there is no coexistence. So we start with random distribution, we end up on cluster or a condensate, all the particle comes to the same point. But is it possible to have a coexistence of the cluster or the gas in the system? To study that, we modify the model a bit. We consider the evaporation, or we put the noise in the model. So then let's say we start with a cluster of some size n. All the particles are together. And then because there is noise, at some point one particle will come out. There will be evaporation. So you can see after some time, one of them, it's coming out. So then another particle will come out. So one can calculate the rate out from a cluster of size n. So that's what we are plotting here now. So this is the size of the clusters, and this is the rate out. And we are plotting in log linear. So the linear means is exponential. So the rate out is exponentially decreasing. That means the evaporation time is exponentially increasing from a cluster. And this problem we can understand, or we can relate with the Kramer's problem. If you put a particle in the potential oil, what is the rate out from the potential oil, and that goes exponential rate out. And here also we can write the like the equation of the center of mass of the cluster, and there, because these are attraction between the particles. So if you put more and more particle in the cluster, the potential will become more and more stiff, and it becomes more difficult for the particle to come out from the cluster. So that makes the exponential function of the rate out from the cluster. So that means even in presence of noise, we are not getting the coexistence. Either we'll get complete gas, or we'll get complete condensate or the cluster. So now next thing, so far no coexistence in the system. So what can we do after to have a coexistence? Let's try with the repulsion. So now we starting to consider the volume exclusion of the particle. So there was only attraction before, now we put the repulsion also. So now the potential is modified. So there, when particles come very close to each other, they will repel, and when they go a bit far away, they will attract. So, and this is again short range interaction. So there is a cutoff. Beyond this point, they will not interact. And so now if we start with a homogeneous distribution of particle, it will form a condensate and a background gas, but it's numerically a bit expensive. It will take a long time because they get very localized. This is harmonic potential, so makes simulation very slow. So now to start, we want to estimate a steady state, and we want to start the simulation from that point. So to get that idea, like where we can get a steady state, we consider any size of a condensate, and we calculate rate out from that condensate for different size of the condensate. And we consider a gas in the system, and we define a condensate point, and we are calculating rate in for a given density of the gas. So for a given density of the gas, what is the rate in? So now we are kind of, okay, let's say we consider this size of the condensate. So what is the corresponding rate in? And so we will consider that kind of close to that gas density in the background. So now we start simulation considering the size of condensate, let's say 1000 here, and background gas density is this is very dilute. So now if we let the system evolve over time, so we see it's a steady state of the system. So there exists a coexistence between a condensate and a gas. So the volume exclusion or repulsion between the particle leads to the coexistence for the system. Now the next part of the model is So we start with the initial random distribution. So this is the density profile again using the exponential function color. So we are starting with a homogeneous distribution of the particle, and then we find a small condensate in the system, and the background is a coexistence. Now we are doing like, okay, so we start with this. If you follow the red symbols here, so there is no coexistence up to this point. Then suddenly there is a coexistence of condensate and gas. And now what we are doing, we pump in more particles in the system, and let's see what happens. So then we put more particles, and we see the particles in the condensate is increasing, not in the gas. So that's like, if you follow this, so we are pumping in more particles, and the particle goes to the condensate because the cross. So there is also an interesting thing about harmonic potential, because if you make the repulsion strength very high, they will make a like crystal-like structure. But for the intermediate regime, they can compress the cluster a lot, the like infinitely compressible cluster, and then they can accumulate a lot of particles in the cluster without changing the cross section of the cluster. So that's why the size of the condensate is increasing, but not the density in the gas. And you can start in the reverse way also, like let's start with one condensate, and then you take out particle from that, and you will find the coexistence of the condensate and gas. So now this behavior is quite fascinating for us, because now you can plot the size of the condensate for the different strength of the noise or the evaporation that you can map as a temperature of the system. And we see there is a linear behavior with this functional form and the ratio of the particle in the condensate and the total number of particles in the system n. So this kind of relation is very well known in the literature of quantum, in terms of in quantum system, like Bose-Einstein condensation behavior. So our claim is like, so active matter system can show similar behavior for when we consider this kind of potential or the interaction of the potential. So they show the similar Beck-like behavior. So far, I have not considered the velocity alignment interaction. So for this last model, there was no emergence of ordering in the system. So they only phase separate. Now we will consider the velocity alignment interaction in the model. So the position update equation remains same. This is active force term. This is the interaction between particles, and this is the evaporation in the system, what we have considered in the last model also. Now the new term appear here is the velocity alignment interaction, and this is the noise in the orientation. So there are already in the literature known different kind of velocity alignment interaction. So one is additive interaction. So it's not normalized with the number of neighbors. And another is the non-additive interaction. So omega I is the number of neighbors inside the interaction radius. So you normalize it omega I. So now I show the video for this. So now here we call two different model 2 and model 3. And I mentioned one thing also, like this model will, if we tune this d theta, it will go from the polar order state to disorder state. So it will have different behavior at different. So for small d theta, it will show similar behavior with this model 2. And when d theta is high or the disorder is noise strength is high, it will be disorder system, and then the behavior will be different. Yes. Now we are always considering that, yes, repulsion. Yeah. So now you start with again the initial random distribution of the particle, but because of attraction repulsion, they come and they glue. But now the interesting thing, if you will follow this cluster, when it is growing in size, they are becoming more persistent. So cluster is growing in size, and their persistent time or persistent length is growing with this size. So that's the important feature of this model. The cluster becomes more persistent as it grows in size. So now to understand this behavior, okay, so how can we understand the persistent time or persistent length of the cluster? One can calculate the velocity autocorrelation function for the cluster of different sizes. For model 2 and model 3, I'm writing the order side, because then these two models are similar. They are polar order. Because they are doing the velocity alignment interaction that emerges the ordering in the system. And now for the different size of the cluster, 2, 4, 8 particles cluster up to some 256. So this is 2 particles for, so the correlation time is increasing with the size of the cluster. Also for model 3, the correlation time is increasing with the size of the cluster. So this is the one can feed with the exponential function. This is log linear scale. So if one can feed with the exponential function and can estimate the persistent time of the cluster, and that follows the linear relationship with the size, with its size. So one can write down the equation for the polarization field of the cluster. So this goes, this term is for the mean field order disorder phase transition, and this is the noise strength, and the strength of the noise is actually linearly decaying with its size. So then again, using the Green-Kubo relation, one can get the mean square displacement or the diffusion constant of the cluster. So this is for model 2 and model 3. You can see this, the diffusion constant is linearly increasing with its size. But as I was mentioning, when there is high noise in the system, model 3 becomes disorder. So then the diffusion constant is decreasing linearly with its size. So this behavior is same as the model 1, the first model I was discussing about the diffusive particle. So there also the diffusion constant is decreasing with its size. Now the next thing is to understand the coarsening behavior of these two models. So then again we can define the collision rate, and that will depend on the the propulsion speed of the particles or the cluster and the cross section of the cluster, but it's a constant here because it's not growing in the limit we are working, and the density of the clusters in the system. So density of the cluster, one can like number of clusters over the area of the system, and then we can write the evolution equation or for the clusters, number of clusters in the system, and we can do the similar calculations, and that gives the linear or the ballistic aggregation of the cluster. So now the coarsening phenomena is different. It's previously it was diffusive aggregation. Now we get the ballistic aggregation because the cluster, and also it's important because initially it's not ballistic. So cluster has to be like what I said, when the cluster is growing in size, they are becoming more persistent. So they are going to the ballistic regime. So the aggregation will be ballistic. And now for the model 3, we can have both things, like when they are polar order state, they give this rise to the ballistic aggregation. And for the polar disorder state, this is the diffusive aggregation of the particle. And then we do the similar study for the Beck-like behavior. So there we find there is again coexistence, and the cluster is highly persistent. So we are putting arrows, like they keep on moving in the same direction for a long time. And one can get the coexistence for this model also. Yeah, this video you can see. So this is a bit different from the, like you see the condensate is moving persistently, and it will absorb particle, and because of the repulsion and evaporation, it will keep on, like particle also will come out of the cluster, and there exists coexistence. But still we are still studying this phenomena because we have, I mean, for the other model, we have seen the linear behavior with the ratio with number of particle in the condensate and with the noise strength, but this is still not, like, we are studying still, but not, I mean, not very clear, like what kind of relation it will follow. So now for this part of the talk, I will summarize, like, okay, so previously it was known there is an emergence of ordering in the active systems, and there is band formation, for a lot of studies about band formation, phase separation. But in this study, our claim is there is no, if we consider this kind of interaction in the active matter system, there is no polar band formation, and this fluctuation or the order phase are different from the what is known in the literature, those systems, different from those systems. And one can characterize the phase transition behavior in this kind of interaction. Also, the main claim from this study is there exists two different kind of phase separation phenomena or the coarsening phenomena, that the condensation classes, like either they can be diffusive condensation or diffusive phase separation, or in presence of velocity alignment, there will be ballistic aggregation of the cluster, or like this is another class of condensation. So now I will briefly discuss about another study, what we are doing. This I have already mentioned. This is a different kind of particles. So again, so they are, so if you track any trajectory, then you will get the rotation clockwise, anti-clockwise, And this is I bit more explain the particle here, like this side is coated with the TiO2 and other side is coated with the gold, and they are immersed in a hydrogen peroxide solution. And in presence of UV light, there is a chemical reaction, and that makes the particle active, like they starts to move, and when they move, they are moving, they do rotate, and they. So now, yes, this is it.
What is TO2?
TiO2, titanium dioxide. So yeah, like the full disc is titanium dioxide. Then they coat one side with the gold, and to make them asymmetric. So this side reacts with the light and makes it dissolve the hydrogen peroxide, because the solution is hydrogen peroxide and a water mixture, and this makes the H plus and O oxygen, and there is a release of energy there. And this side is in presence of hydrogen peroxide, because there is also excitation of electron from valence to conduction band, and they flow towards this direction, and the H plus ion comes here and make the H2O2e and H plus, they make water, so that this energy release force this particle to move. So now the thing, okay, we take a trajectory over a long time from the experiment, and now we can, because we know the coordinates at each time. So in the recording of the trajectory, we know the coordinates of the particle. So we can define all the things, the orientation of the particle, velocity, direction of the particle. We can calculate the angular velocity omega of the particle. So the interesting thing is the angular velocity. So you see the angular velocity, they rotate in both directions, clockwise and anti-clockwise. Now, if you look at the trajectory here, so this particle is rotating in the clockwise. This is from this part of the trajectory. And if you zoom another part of the trajectory, they are rotating in the counterclockwise. So this is quite interesting phenomena. And so then we are trying to model what kind of model we can use to understand this behavior. So again, one can write the position update equation, the active force, because they are active particle moving with a speed v0. Although in experiment, the v0 is not constant. There is a fluctuation in the v0 also. But we are studying the effect of fluctuation. Without fluctuation, how much the diffusion constant is changing. So we can ignore the fluctuation in v0. And then this E is the unit vector, direction vector, that depends on the orientation of the particle. And also one can write then the theta update equation, that because this is the chemically driven particle. So the translational motion and the angular velocity is coupled. So if the particle is moving higher speed, they will make a bigger circle to rotate. And when the speed is small, they will rotate and localize, and they will rotate on the cell. So that's why you're putting the V0 here. So that makes the curvature depending on the cell propulsion speed, and the omega is the angular velocity of the particle. And this is the Ornstein-Uhlenbeck process. So what is this? Because there is a relax. So you start with an angular velocity, and the kappa makes the relaxation. You relax is to the zero angular velocity, but this term will make you either positive or negative. So you change your sign of the angular velocity depending on the noise in the. So now you see in a trajectory. So if the relaxation is very high, so that means you will move more in straight line. And now if you tune the parameter, so you start rotating in different directions. So you change your chirality. So these particles are not chiral, so they are rotating particles. So they can change clockwise to anti-clockwise. So also for a very low kappa value, so like this or this one, they rotate in one direction, they comes out of that thing and rotate in the other direction in another circle. So which is very similar to the thing we have seen in the experiment. Now we took the experimental data. So we know for persistent particle, the velocity autocorrelation fits with the exponential function. So, but we are plotting here from the experimental data velocity autocorrelation, but it's not linear. So it's not the persistent particle. And there is actually existing literature about this kind of Ornstein-Uhlenbeck process and velocity. This is a theoretical calculation where it fits with the double exponential instead of a persistent particle with one exponential particle. So we try to fit the parameters. So we are extracting all the parameters like d omega, fluctuation in omega in the experiment, cell propulsion speed, and the cell propulsion speed. Everything is extracted from the experimental data. Only thing we are fitting is the kappa relaxation. So one can tune the kappa and the fit with the velocity autocorrelation, and it goes very well with the double exponential. So far I have talked about the dynamics of a single particle and how we can understand of this kind of experimental system. And also, like, still this is also an ongoing study, but few interesting behavior we are seeing, we observe in the system. That's like I kind of mentioning those behavior. Like, okay, so I have considered one particle and look at the dynamics of the concept. Now if you consider the interaction between the particle, so here this is again from the experiment. So the black, this is the trajectory for one particle is coming and rotating, the black one, and this arrow shows the direction of the particle, and the red one is also the particle 2 or coming and rotating in this direction. So this is the point when they come and they interact, they glue, because of there is attraction, and this attraction is coming because of there is a concentration of electron and the hydrogen plus, and that leads to some electrostatic attraction in the system, and they glue. So then the green one is the trajectory of the center of mass. So when they glue and they keep on rotating with the average angular speed. So this is from the experimental data, like particle 1 is fluctuating around some average. So before actually what happens, so the locking of omega depends on the instantaneous angular speed. So the angular speed they have before the collision, they just get locked with that angular speed. So now we are kind of demonstrating this with the new simulation model. So the particle 1 is rotating like this, come here, the red particle is rotating with the smaller, like higher omega, smaller curvature, and the green one is the center of mass of the two particle cluster. So they come and glue, get locked with the average. So if there is no noise in the system, they will forever rotating in the, they become chiral, the cluster become chiral in absence of the noise. But if of course there is a noise in the experiment, so now if you consider a noise in this system, they'll rotate and they may change the chirality, but for low enough noise they can keep on rotating for a long time. So this is a cute observation in the system. Like, you start with the rotating particle, they are not chiral, but because of the interaction, the cluster becomes chiral. So this comes to the end of my talk. So this is the group of Fernando in COI Sergi Paris University, and thank you for your attention, and I will be very happy to answer the questions.
Thank you, Zurita. Any question? No question. You show us some phase transition who was first order, no? Can you tell us a little bit more in the first part of the talk?
Yeah.
So there was some kind of hysteresis loop, no? There, no?
Yes, exactly. Oh,
can you explain better?
Yeah. Okay, I go back. Yes, yeah. So this hysteresis loop.
Yeah.
So, okay, for the red, the squares or these things, we start with a homogeneous distribution of the particle, and there is a spontaneous emergence of the condensate and the gas. So you need a sufficient fluctuation in the system to form the condensate, because this is not the persistent particle, they are diffusive particle. But for other model, there will be no hysteresis in the system that we have seen, because here they are diffusive particles. So once you have a form of the small cluster, you need more particle to come to that point, because we are working kind of a dilute regime. So you need a sufficient density fluctuation to form a seed or the condensate. So because that's why this is like, you have to go a bit higher in the density to form a spontaneous condensate, and they keep on growing. But for other way around, you have already a condensate and the particle is, we are taking away particle. So they like even the low density fluctuation or the things, because we have already a condensate there, and that leads to the hysteresis. So, but for the model we are considering the velocity alignment interaction of the persistent particles, they will keep on moving, and they will make the seed even for the low density of the particle.
Okay.
And nature of transition, I think it will be different because this is more like a passive systems, because they are diffusive particles.
Yeah. Okay. Any more question? Tobias?
So you drew an analogy to Bose-Einstein condensation there on the slide, right?
Yeah.
But Bose-Einstein condensation is a quantum effect, right?
Exactly.
So how far does this go? I mean, is this analogy, or is it just this is
Yeah.
a condensation? But I'm not sure I would relate this to Bose-Einstein, to be honest.
Because physics is very different. I agree, because we don't have any energy state or ground state energy minimization. We don't have for the active matter system, because it's extremely difficult to write a free energy functional for this kind of system. But the main point we want to mention, okay, so even the definition of temperature is not very well defined for active matter system. So many literature we define like effective temperature or like, but the noise we kind of analogous to the temperature of the system, and like the quantum system, one can make analogy with the noise strength as a temperature of the system. And the observation is it's follow the similar relation. Maybe the physics is completely different, but we are kind of making an analogy like, okay, so if we define this as a temperature or effective temperature of the system, and the behavior or the response of the system is similar, like we are calling it Bose-Einstein like, not like, not Bose.
But then by that definition, any condensation is Bose-Einstein like.
But then has to follow this relation, linear relation. If the system follows this kind of relation, maybe like one can say the Beck like or something. Yeah.
Any more questions? Oh, we found Sudipta again. Thank you, Sudipta.
Thank
We will be here this afternoon. If someone is interesting to talk with him, he will be in my office.